Okay, welcome back. In the last video, we talked about Hooke's law and how it relates to this example of pulling a steel rod with some sort of force. So we're going to focus our studies on this linear region in the case where if you were to pull on this rod with some sort of force F, that up to a certain point, the relationship will remain linear. So if you were to let go of the rod, it would snap back down to its original position, or this original length L. So this applied very well for the case where we had a steel rod with some sort of a length and some sort of a cross-sectional area, and the rod itself was made out of a certain material, in this case steel. But we want to try to generalize Hooke's law and how it applies to materials in general at the molecular level or the atomic level. So if you were to look at the molecular bonds between molecules, how could we sort of apply Hooke's law and understand its relationship with these molecular bonds without having to worry about this L or the cross-sectional area or the fact that it's made out of steel? What if we just had some general solid with some arbitrary length L and arbitrary cross-sectional area, or if it was just a clump of material? How can we generalize Hooke's law to that scale? Well, we have to get down to the molecular level. So I'm going to first draw out this rod and its cross-sectional area down here. So again, this is the same rod, and I'm going to draw this a little bit bigger, so we're just zooming in. And the cross-sectional area in this case is circular. And we know that if we applied that force F here, that force is going to distribute amongst this entire cross-sectional area. Now, if we're talking about the molecular level, intuitively we can understand that the number of molecules on that cross-sectional area is directly proportional to the area. So in other words, the bigger this cross-sectional area is, the more molecules there are of that material, right? So I'm just going to draw a few molecules here just to kind of represent that this cross-sectional area has molecules, right? This is a solid. And if we were to apply this force F to this cross-sectional area, then F really is distributed among the molecular spring bonds and is really proportional to F over A. In other words, this force F is going to be distributed amongst that area, and so each molecule is going to take a portion of that force F. And since each molecule is taking a portion of that F, each molecular bond is going to take a portion of that force. Okay, that makes sense. The number of molecules on a cross-sectional area is directly proportional to that area. So the bigger the area, the more molecules there are going to be. And the smaller the area, the less molecules there are going to be. So again, I said that the force pulling each of these molecular bonds is proportional to F over A. So from this relationship alone, you can see that if we were to increase the area A and make it really, really big, but keep the force the same, each molecular bond is going to take a smaller and smaller amount of that force. However, if we made the A very, very tiny, then this force is going to be distributed over only the molecules on that cross-sectional area. And because the area is much smaller, there's less molecules. So each molecular bond has to take more of this force. In other words, the bigger the area, the more molecules and molecular bonds, hence the less force each bond has to take. So again, each of these molecules have a molecular bond with other molecules around its area. And the force pulling on each of these bonds is directly proportional to how much that bond stretches. The higher the force for each of these molecules or the molecular bonds, the more it's going to stretch. That makes sense, right? If we take this force and we increase it, the rod is going to stretch even more. But because we're talking about the molecules and the molecular bonds, we know that if we increase F, each of these bonds or these molecular bonds right here, here, and here, those are going to stretch more and more. Okay, so that's a pretty good relationship between the force and the area. How about the length of the rod and the molecular bonds there? So we can intuitively understand that the number of bonds and the number of molecules along the length of the rod is going to be proportional to its length. So the greater this rod is, the more molecules there are and the more molecular bonds there are. And the shorter the rod, the less molecules there are and the less molecular bonds there are. So if we were to stretch the rod by some length delta L, then the stretch of each of those bonds is proportional to delta L over L. Another way to think of it is that this force being applied to the rod causes each one of the bonds to stretch by an amount that is proportional to delta L over L. So another way to think of that relationship is if we looked at the length of this rod, we know that the longer the L, the more molecules there are going to be along the length of that rod. And the more molecules there are, the more bonds there are. So let's go and make this a little bit bigger. Let's zoom in here. And we can kind of see that each of these molecules have some sort of molecular bond, right? And the longer this distance L, the more bonds and molecules there are going to be, right? And the shorter this rod, the less molecules and molecular bonds there are going to be. So another way to think of this is that this ratio right here, delta L over L, is going to be directly proportional to how much each of these bonds stretch. So the higher the value, the higher each bond will stretch. And the lower this value, the less each bond will stretch. So both of these ratios right here tell us one very important thing. And that is how Hooke's law, this Hooke's law, is applied to this molecular level. And it simply tells us that the force pulling on a bond is directly proportional to the amount that that bond stretches. Now, just as we derived Hooke's law by looking at the slope of this linear region, and remember, all of this discussion right here, we are focusing around the linear region. So we're not looking at anything past this linear region here. We're only studying the linear region. So how can we use these two values to understand the relationship between force and this stretching at a molecular level? Well, just as we did here to figure out what Hooke's law was, we can look at the slope, right? Slope is F over delta L. And because the force that's pulling on this material or the bond is directly proportional to the amount that that bond stretches, we know that F over A is going to be directly proportional to delta L over L. And we can write this relationship as F over A is equal to this thing called Y, which is Young's modulus, times delta L over L. So just like force was directly proportional to delta L by some proportionality constant that we called K, this value of F over A is directly proportional to this value of delta L over L by this proportionality constant called Y, which is Young's modulus. And Young's modulus is directly related to the spring constant of each of these molecular bonds that we were looking at. So Young's modulus doesn't really care about the composition and the geometry of this material. All it really cares about is what the relationship between the force and the molecular bond is at a very atomic level.